So today we have two sessions. The first session deals on packaging, assembly, and test. And we will have 4 speakers. First one is Ignazio Piacentini from ficontec service. So please. Right now? Okay.
Can you hear me now?
Yeah.
Yes. Good morning, everyone. Thank you, Pasquale, for having me here. You will have noticed that I'm not Thorsten Fahrenkamp. My CEO is somewhere flying to China, and he asked me to replace him, and I have half an hour to talk to you. So I modified the title slightly, so replacing optics with PICs, because it's about photonics, integrated circuits, that we are going to talk about. So I have 30 minutes, and what I would like to share you is basically a few things that have changed and the growth that ficontec has witnessed over the last couple of years. I've been giving several speeches over the last few years. In 2016, I was talking at PIC International about automated assembly. I've been talking about test equipment, and the last 2 years have been really a very, very rapid growth for the company, with also some inevitable growing headaches. Delivery was one of the issues, and we are really being pushed by the market to the next generation of manufacturing machines. So that's what I'm going to share with you. So I've stolen a sentence from Arne of Lyonics. So our mission is, well, our machine build your PICs, and Arne yesterday was saying our chips drive your business. And we are an SME, a small company in northern Germany. And we would love to have totally standard machines, but photonics is nowhere close to any standard. So what I like always to say is that our machines are really the embodiment of a customer need. So we always start with an analysis of the process needs of a customer, and we build machines out of a kind of a Lego system of different parts. And a message is also from lab to fab. We very often step into the early phase of manufacturing when products are still in a very small volume, maybe in lab, and then we can go all the way to large volume manufacturing. We are about 200 people, probably a bit over by now, and we have about 700 machines installed worldwide. And last year, I think we delivered about 140 machines. Not so sure about this number, depends whether the machine actually exited the company on the 31st of December or not. This page I will skip. We really cover a broad range of photonics products, from power laser diode stack assembly to very complex transceivers and other devices in photonics. But you have a link to the page, and you can go and look for some details there. As you can hear from my accent, I'm Italian in origin, graduated in UK, living in Germany. And when I joined the company, I asked, is this a German company? And my colleague said, of course it's a German company. So, well, you know, we got 95% of export. We are really a global company that by mistake is in the north of Germany, so you better adapt to that. So we really export a lot, especially in Southeast Asia, although very often we still transit via North America in order to reach manufacturing in Southeast Asia with very large names. The growth of last year forced us, and the year before, forced us to start differentiating between repeat large multiple machine orders and special machines. So the repeat orders today are manufactured in a base in Estonia, where we are also part of our design engineers, while we retain in Germany the headquarters of the factory acceptance testing and all the special projects. And we really have been putting some effort in reducing delivery time, which has become one of our major issues with our customers, and through a more modular design, better procurement, and so forth. At one point, it was very difficult to get a granite basis or even cameras. The market was being very active in photonics and so forth. So, and talking about the company growth, I share some numbers of machines. I joined the company only in 2015, mid of 2015, and moving from PI, from a physics instrument, where I worked for a few years before. And you see the number of machines. And 219, they're actually machines that are already on order. So in a way, without the contribution of sales this year. And what is interesting is the share, the market share of the machines in 2018. 80% is still driven by telecom, datacom. 50% is a LiDAR assembly. And 5% is what I call the weird and wonderful, which are the projects I really like, and normally I follow them personally. What is interesting about LiDAR is that this 15% was really a quantum jump over a period of less than 1 year. So LiDARs have been around for a while, but it's only now that they're really moving to numbers. So we are really thankful that photonics came back for me in 2013 with telecom and datacom, but certainly the emerging photonics market segments are probably the ones that are most interesting. So not only datacom and telecom, as I was saying, but certainly autonomous vehicles and LiDAR, augmented reality, virtual reality, or what now they like to call mixed realities. Biomedical medtech is certainly growing photonics. Sensing can be seen as whatever we could squeeze on an optical bench when we were students, now more or less can be squeezed on a chip. So that is really what is bringing photonics into sensing. And of course, there is RF photonics, aerospace application, and so forth, and even IoT and consumer goods. Talking about a very specific market segment that is medtech and sensing, the challenge here is really scalability. So it's quite easy to, well, not easy, but you can put some effort in developing devices, but very often these devices are one-off. And so going from an early phase of a few handcrafted devices to large volume is really a game of scalability. And I think Pim Cat from Technobis was mentioning sensing, keeping away for microfluidics and the messy part of the chips, but there are also companies, of course, that do get into the messy business of mixing photonics with microfluidics. A few words on packaging. So packaging is really doing whatever it takes from going from wafer level, from a single chip to whatever is required to have a full functional device. And this brings us to hybrid assembly and fiber pigtailing, which are really the two things that I call bothersome in the assembly process, and also in a way the fortune of ficontec. So you cannot have everything on silicon photonics. Silicon photonics has been really driving the growth of photonics, but you cannot produce lasers on silicon, so you always have an external source somewhat, and you always have to get your optical signal in and out of the chip, so you have some kind of pigtailing. You need very high placement accuracies, and you need to ensure these accuracies post-bond over the complete lifetime of the device. Talking about assembly and testing, this introduces the question of cost. This slide, I think, was produced in 2006 at MIT in Boston, has been used over and over again, not only by me, but also by Peter O'Brien or all our colleagues, including the one that are not here today. I'm not sure that this slide is still current. Maybe it needs a bit of readjusting, but even if it is wrong, we compare basically cost of packaging in the semiconductor world, which is about 10-12% per device, to the staggering cost of up to 80% for packaging of photonics devices. So the three top bars are really about assembly, packaging, and testing. And we, of course, believe that the only way out of that is to automate these processes in order to reduce the cost. So active alignment and passive alignment is something that always come up during my presentation and speeches, very often with some healthy discussion in the audience. I think, frankly, that is a bit of an overinflated debate. The active alignment is what guarantees submicron accuracy. You cannot really go below let's say, the boundary of the 1 micron without active alignment, but is only one step in the whole process. This is a very old slide. In 2002, I was working for National Instruments in Austin, Texas, the people of love you. And we had a small group that was already looking into photonics automated assembly. And the wording was a bit different. Instead of active and passive, we were talking about coarse alignment, fine alignment. And the third one from the right is me in Cork at Flextronics. They were just about to open a factory in China. It never happened. The market went disappeared basically in the beginning of 2003. But all these bubbles and boxes that are essentially still there. Flexibility versus speed is really a matter of volume. I will not comment this slide, but basically you go from tens of minutes or even hours in a totally manual assembly to a few minutes today, and most likely tens of seconds when volumes will really pick up speed. This slide somewhat oversimplified. It doesn't really take care of the device complexity. That's why I added a little detail of a free space micro optics. Each lens is about 1 millimeter in square size. And so, of course, it also means changing a bit the philosophy of our machines and moving from very complex machine that can do many different processes with a great flexibility to more streamlined sort of sequence of machines which can take care of simpler but much faster processes. In doing all of this, we can certainly borrow from other industrial segments. Basically, I've been away from photonics from 2003 until 2013, and in this decade, I was really doing totally different things. I was involved in advanced robotics and machine vision. And so very often engineering works in tight compartment. We don't really sort of cross-feed between engineering segments. So adopting this means using established industrial solution. And you see here a first example of inline machines. There are only two, and I have a short video clip of these two machines assembling a rather complex transceiver. So, of course, this machine has to be clean room compatible, but you can adopt a lot of bits and pieces from other industrial segments. So let's speed up a bit. This is a video clip that show. I lost my cursor. So just a second. This is a 3 minutes video clip. Most likely we will not use all of it, but it shows basically there are two machines in a sequence doing different bits of the same assembly process, picking up micro-optical elements that is a gel pack size. You can push out a tray of small PCBs where the transceiver is mounted. is automatically connecting an array of fiber. You need to actually connect the outer fiber to do some active alignment. Is placing the component. You see a gripper holding a fiber on the right-hand side. This is actually a bundle of fibers. Is purging the glue dispenser. It has already done a dry run without the glue. The glue has been placed, and then you flush with your UV curing. This is just part of the process. You disconnect your connector, move away, the tray moves out, a new tray comes in, you get the gist, and it continues on. The video clip is a bit longer, but I will not bother you with all of it. So there is certainly a need to move to a wafer level assembly, and this is a fairly large complex machine where we had experienced some problems. It's a machine that is really dedicated to a lab in Pisa at Infotech. It has 2 full 12-inch wafers, so you can pick up parts from a singulated diced wafer and bring parts onto a non-diced wafer for wafer level assembly. It can do active alignment, it can do passive alignment, it can use epoxy bonding, it can use a laser welding, exploiting the fact you can shine a laser in the infrared from underneath a wafer to do some laser-based soldering. Still an ongoing project. Where we got stuck was really on ensuring passive alignment down to plus minus 1 micron across, not on a single device, that we've done it already, but actually across a complete 12-inch wafer. It means moving large distances, keeping passive alignment. Similarly to the need to move to a wafer level assembly, there is an increasing need to move to wafer level testing. This was a project that we landed for AIM Photonics in the United States a bit over a year ago, and that is really a project that is tackling the testing of complex wafer over large temperature cycles, so presumably also for military-grade devices. And testing at wafer level with grating couplings is fairly easy. The light shines upwards, so it's quite easy to couple your fibers. It's a different matter when you have edge coupling devices. So the only way to do edge coupling at wafer level is to cut grooves, have trenches, and you see in the picture, you see actually an angled array of fibers on a tip which is being inserted into a groove. It also means that you are very close to collision by definition. So you're entering a groove, you're stopping a few tenths of microns from the bottom of the wafers. A 12-inch wafer is by no means flat, it's fairly curved, so there are a lot of mechanical interesting issues to solve. And one of the key points is to combine electrical and optical testing, and that is most likely one of the top challenging issues. How do you combine both electrical and optical for devices that keep changing? So you have to supply also specific probes for specific devices. You see here the implementation of such a machine. If you're familiar with PI physics instrument, you will notice there are a couple of hexapods plus 2 piezo cubes hanging upside down. We prefer this kind of configuration, and the difference is that you can buy a subsystem from PI, but we are in the business of supplying turnkey complete solution. So there is a lot that you have to add, but they're certainly quite nice devices. Maybe one objection, I don't know whether Thomas is here in the room. Hi, Thomas is an ex-colleague from PI. We are quibbling a bit on the cost of these beautiful devices because we have to integrate with a lot of other hardware, and we have some kind of fixed target price for our market. You see another example of use. This is Southampton University. They have a nice concept of erasable grating, so I call their erasable grating an optical test point. You can test on a grating, so you can test vertically, and then you can, of course, if you have an optical input-output, automatically you have losses, you are throwing away some light, but after your testing, you can anneal it with the laser, so basically you erase your coupling, you check the functionality of the circuit, and you move on. There is a short video clip here. We are measuring the distance from the wafer. It's very difficult to see the fibers on the tips. You can just about see one fiber shining on the right-hand side. It's not yet a full-size wafer. You see a smaller wafer on a much larger chuck. It's a very early video clip when we are still testing the machine. You see the specular reflection on the wafer. And you see what is seen through the microscope of the machine. So you see this is a totally passive wafer that was actually developed purely for testing the machine. You see the two tips coming in close proximity, and you see them wobbling around, looking for the maximum peak coupling. So the electrical part is not mounted yet. There will be also some electrical probing in parallel with the optical one. For those that are interested in the bits of pieces of the machine, I've not been talking about what are the ingredients of the machine. It would be a rather lengthy, well over half an hour speech. But if you are interested in what are the key bits and pieces for the machine, you can download a chapter of this book from our web. I think I wrote this chapter together with Thorsten. I think I started when I was still in PI, actually, so probably was 2014. So it's becoming rapidly obsolete. Things move on quite fast. It was published almost 2 years later. But it's still, the list of parts is still valid. And the last line in bold character is about software. I've not shown you anything about the software and the application software aspects, but certainly an operator does not see the beauty of the mechanical bits and pieces. It only sees the software interface. So it has to sequence a complex process. It has to tweak and adapt a process. So the software is a fundamental part of the machine. And ficontec has been able to stick to the same software, make it backward compatible. So the software platform is common to more than 700 machines, and it comes with a rather complex sequence. The top layer is LabVIEW, which makes it quite easy to customize also directly from the customers, and allows to add, for instance, quite easy instrumentations, and also to generate, let's say, database information if you have to check the quality of your production. So I wanted to leave just a couple of minutes for a question, maybe, so I come to my last slide. The first comment probably annoys my CEO because we are still trying to figure out what kind of company we are. We would love to be a pure equipment manufacturing company in large volumes. I think we are a crossbreed between a super specialized system integrator and a machine manufacturer. I would say that this being flexible and answering to the need of our customer is also intrinsically the reason for the success of ficontec, and is something that the company, even in its growth, should keep as part of the company heritage. We need to talk to our customers, so if any of you has issues, contact us at the early stage. It takes a while to build a machine for your needs, so the earlier we start, the better. I think that volume manufacturing is just starting now, and standards will eventually come, but it will take a while. And our capability to adapt to growing requirements will also determine very much the success of ficontec. And the last line probably will introduce the next speaker, Gunther Wollrath, and is about speed, or you can also say cost per part. So with this, I finish my presentation, I think in 25 minutes, so we have a few minutes for talks, and I would ask Silvano, a newcomer in a company, to stand up, wave his hand. Silvano joined, he has an Italian family name like me, but he's actually French, and he will take care of Europe and especially Southern Europe. So I would love to have some large photonic center whisking me away from gray Bremen back to the south, so engage me. Thank you very much for listening to me.
Okay, thank you, Ignazio, for your very nice presentation. I feel there are going to be questions.
Yeah, it's actually a short question.
Yeah.
On your last slide, you talk about volume. So what is your exact definition of volume, and which markets actually meet that volume already?
It's a rather tough question. Volume means different things for different people. If I talk about, for instance, the example of medtech, we are talking about. I've lost my phone. Oh. Okay, so we are really talking about 100,000 pieces per year. If you are talking about a transceiver, we are still in the tens of thousands. But basically, I would say that a large volume is, is anything, in my opinion, above 10K per year, all the way to the hundreds of Ks and possibly the millions. Then I will take 1 minute to add a comment to your question. I think there is a great need for what I call intermediate volume manufacturing. That is something that is missing on the market. There are a few players in the audience actually that have been starting to think of offering services, and basically from people that go from few tens of pieces in the lab into these intermediate, from the few hundreds to the few thousand. Eventually they will scale up, so they are sort of transiting customers, and the difficult part is to follow this customer and pave the way to really large volumes. Does this give you an answer on the volumes? Well, what are the volumes you have in mind? Can I ask you what you think is a large volume?
No, I mean, I would agree with these numbers. I'm just wondering when you would make the transition from, let's say, the more traditional 10 years ago manual packaging to this automated solution. What is the break-even point, so to say?
For us, the transition is already happening. The difference is what is the cycle time of the machine. Our machines, they work with closed doors, automated loading, and a semaphore on top. So if you are a production manager, all you care is to see that the light is green. The difference is that we move from machines that had several tens of minutes per part. The latest one for optimizes processes, they're now in the region of 2, 3, even down to 1 minute for fairly simple complete assembly. So I'm talking about loading, aligning, dry run, dispensing the glue, flashing the UV, unloading.
Okay, thanks, yeah.
Okay, thank you very much. Maybe time for one very fast question.
If you had to prioritize your areas for standardization, could you pick maybe your top 2 or 3 areas to standardize?
Some very simple things which are already happening. First of all, instead of having endless sizes, maybe start defining sizes in steps would be a great beginning. Then deciding north, south, east, west, which side is for electrical connection, which side is for optical connections. Then let me tell you a little anecdote. The first project that brought me to Germany was a test vehicle assembly for ST Microelectronics, just about the only large semicon company in Italy. And they were using the Luxtera laser source, and it was placed very close to the fiber bundle of fiber. So actually picking up the parts was a real pain, down to the grippers. The mechanical design of the grippers was tough. And then I met the designer of the wafer, so a year after the machine was completed. And I asked him, did you really need to keep the optical path that short? And the answer was, I never asked myself such a question. I was only trying to save silicon real estate, so squeezing more chips per wafer. I said, yes, but once you finish with the wafer, you still have to assemble it. So maybe sort of 200 microns longer would have been easier for the assembly. So very, very basic things. I would start with the orientation, and then even simple things like the spacing of the fibers, which is becoming now a constant, and so forth. And of course, this standard do not apply across the whole spectrum. If you're talking about a transceiver, it's fairly easy. If you're talking about a biomedical device with microfluidics, it gets a bit complex. Would you agree on my answer?
Okay, let's thanks Ignazio again and move to the next speaker.
Thank you.